Mastering integer programming. Decision makers hold the power to make or break operational excellence. Who determines the decision variables in an integer programming model, and what factors do they take into account when defining these variables to ensure optimal operational excellence in their integer programming model? In an integer programming model, the decision variables are determined by the modeler or the analyst, who is responsible for formulating the problem and developing a mathematical representation of the real-world situation. The modeler takes into account several factors when defining the decision variables to ensure optimal operational excellence in the integer programming model. Firstly, the modeler identifies the key elements of the problem that need to be optimized, such as production quantities, inventory levels, shipment routes, or workforce assignments. These elements are typically represented as variables in the model, and their values determine the optimal solution. Secondly, the modeler considers the constraints that limit the values of the decision variables. These constraints may be based on physical limitations, regulatory requirements, or organizational policies. For example, in a production planning problem, the modeler may include constraints on the available production capacity, raw material availability, and labor hours. Thirdly, the modeler defines the objective function that needs to be optimized. This function represents the primary goal of the model, such as minimizing costs, maximizing profits, or reducing waste. The objective function is typically a mathematical expression that combines the decision variables in a way that reflects the desired outcome. When defining the decision variables, the modeler takes into account several factors to ensure optimal operational excellence. 1. Relevance. The modeler ensures that the decision variables are relevant to the problem at hand and directly impact the objective function. 2. Feasibility. The modeler verifies that the decision variables can take on feasible values, given the constraints and limitations of the problem. 3. Scalability. The modeler considers the scalability of the decision variables, ensuring that they can be adjusted to accommodate changes in the problem parameters or constraints. 4. Interdependencies. The modeler identifies interdependencies between the decision variables, recognizing that changes in one variable may affect the values of others. 5. Data quality. The modeler ensures that the data used to define the decision variables is accurate, reliable, and relevant to the problem. 6. Model complexity. The modeler balances the complexity of the model with the need for simplicity and solvability, avoiding overly complex models that may be difficult to solve. 7. Domain knowledge. The modeler incorporates domain knowledge and expertise to ensure that the decision variables reflect the real-world situation and are meaningful to stakeholders. By considering these factors, the modeler can define decision variables that accurately represent the problem and ensure optimal operational excellence in the integer programming model. The resulting model provides a powerful tool for decision makers, enabling them to analyze scenarios, evaluate options, and make informed decisions that drive operational efficiency and effectiveness.